Okay, so hello, welcome back. So in this video I want to show you how you can use an oscilloscope and a signal generator in order to measure the inductance of an inductor. And for example, let's say that you have this inductor over here, you have pulled it out of some circuit and you don't know the value of this of the inductance over here, and so you want to measure it. And of course you know that you can use an inductor meter in order to do the same thing, but well, I was playing with these with RL circuits, a resistor and an inductor, and I needed to measure the inductance of some inductors, and of course, well, I didn't have the inductor meter, so I had to come up with a way to do it using a signal generator and the oscilloscope that I had. So now the circuit that I'm using here is basically as a low-pass filter, an RL low-pass filter. An RL low-pass filter. Okay, so basically what this circuit is, you have an inductor over here, and then this inductor is connected to a resistor. This resistor is grounded, and this becomes the input of your circuit. This is the input signal, and this is your output signal, Vf out. So this basically acts like a voltage divider for an AC signal. Some AC signals here comes in, and then some AC signal here goes out, and then the amplitude of this signal is going to change, and you will get some basically, meaning the peak-to-peak voltage over here is going to change. And the way that it changes is that, let's say that this is your L, this is your R. So the way that it changes is that basically, if this is your Vf out, and if you draw a graph of Vf out versus frequency for this circuit, this is the input frequency. If you draw the output voltage versus frequency as you increase your frequency, so what happens is that as you increase the frequency, the reactance of this inductor is going to increase, meaning that you know that X of L, which is the reactance of an inductor, is equal to 2 pi FL. So this is 2 pi, which is constant, and F is the frequency, L is the value of inductance. So as you can see, as you increase your frequency over here, your reactance is going to increase. Okay, so now as you increase your frequency over here, basically the reactance of this inductor is going to increase. When the reactance increases, basically the voltage drop across this inductor is going to increase, and so as a result of that, the voltage drop across this resistor is going to decrease. Meaning that at any time, I think the voltage, the incoming voltage here, if you take this as V of in, and the voltage over here as V of L, and the voltage over here as V of out, which is the same thing as the voltage across this resistor, V of R. I think at any point in time, this is the same for capacitors. I mean RC circuits. I'm not sure about this circuit, but it must be the same thing probably. So it's going to be V of in squared is equal to V of L squared plus V of R squared, something like this. But even if that's not true, okay, there is a relationship between the voltage drop across these two, meaning that if the voltage drop across your resistor increases, the voltage drop across your inductor is going to decrease, and vice versa. So what that means is that as you increase your frequency, the inductance of the reactance of this inductor is going to increase, and so the voltage drop, and so as the reactance increases, the voltage drop across this inductor is going to increase. And as the voltage drop over here increases, the voltage drop over here decreases. That means that your output is going to get your output voltage, or V of R, is going to get smaller and smaller as you increase your frequency. Then you will get basically some graph like this, meaning that at lower frequencies you have most of your, you have your full power supply voltage at the output, and then as you increase the frequency, the output signal amplitude is going to decrease and decrease and decrease and get closer and closer to ground. And for the same reason, it's called a low pass filter, because at low frequencies most of your signal is passing through. At high frequencies most of your signal is being suppressed. So that's basically how this circuit works. So now I'm using this circuit in order to basically put the unknown inductor over here with a capacitor that I know with the resistor that I know the resistance of, and then I'll inject some signal over here with some frequency, some peak-to-peak voltage, and then I measure the output, basically peak-to-peak voltage over here, and then put that in, use all of that in a couple of equations, and then I will get the inductance of this inductor. Now how that works is that basically the voltage drop across this resistor, which is your V of out as well, is equal to V of out in this circuit is equal to the value of this resistor, which is R, over the impedance of this circuit, which is the total resistance in this circuit, which is called basically impedance, or Z, times V of in, okay, times V of in. So this is your input voltage, this is your output voltage, this is the value of the resistor, and this is your total resistance in the circuit, which is impedance. Now this impedance is, the way that you can calculate that is equal to basically is equal to the square root of x of L squared plus R squared. Okay, and as we mentioned here, x of L is equal to 2 pi fL. Okay, so what you can do is that use this equation up here and write it as V of out is equal to R over Z, which is basically this thing, and instead of x of L, so over here instead of x of L I can write 2 pi fL. So the square root of 2 pi fL whole squared plus R squared. So I can write this thing over here, which is basically the same thing as the square root of 4 pi squared f squared L squared plus r squared. So I can write this thing over here, so that is 4 pi squared f squared L squared plus r squared. Okay, and that you need to multiply by v of e. Okay, now what you need to do here is basically I mean, you have to solve for your L here. Now if you don't want to see how I derive this formula, you can basically skip forward a few, probably 10-15 minutes or 10 minutes probably, to get the rest of the video. So so now first I can write this as r over the square root of 4 pi squared f squared L squared plus r squared, okay, is equal to basically v of out divided by v of in. V of out divided by v of in. And then what I can do, I want to get rid of this r. I want to get rid of this r, so I multiply everything. So I divide both sides of this equation by r. I divide by r, so I'll divide both sides of this equation by r to get rid of this r. So I will get 1 over the square root of 4 pi squared f squared L squared plus r squared, okay, is equal to v of out times over v of in times 1 by r. Okay, and then if I take the reciprocal of all of this to basically to bring this to the numerator, I'll get 4 pi squared, the square root of 4 pi squared f squared L squared plus r squared is equal to the reciprocal of this, which is v of into v of out times r. So now since I want to get the L out, I raise both sides of this equation to power 2, to the second power. So I get 4 pi squared f squared L squared plus r squared is equal to v of in over v of out whole squared times r squared. Okay, and then you can take this r to the other side of the equation. So that would be 4 pi squared f squared L squared is equal to this thing, which is v of in over v of out whole squared times r squared minus r squared. Okay, and that's the same thing as you can take this r squared out. Let me see. So you can take this r squared out for the sake of simplicity. So I write this as 4 pi squared f squared L squared is equal to v of in divided by v of out, basically whole squared minus 1, and multiply everything by r squared. Okay, and and then I can solve now for L squared. So now L squared is equal to this whole thing divided by 4 pi squared F squared. So that's going to be equal to V of in over V of out whole squared minus 1 times R squared, and then you will divide this by 4 pi squared F squared. Okay, so that is that. Now in order to calculate L itself, L is equal to the square root of this whole thing. So R squared gets out of the, so you can basically write this thing as L squared. You can write it as R squared over 4 pi squared F squared times basically V of in over V of out whole squared minus 1. You can write it this way, and then L is the square root of this whole thing. So the square root of this part is going to be equal to R over 2 pi F times the square root of V of in over V of out whole squared minus 1. Okay, so you can use this formula in order to calculate your L. Of course, only in this circuit, not in any other type of circuit probably. I really don't know if that would work in a, for example, this is a low pass filter. I don't know if this would work in a high pass filter. Okay, so now what I'm going to do is basically connect this filter that I've made, and I'm going to pretend that I don't know the value of this inductor, and then we will figure out the value of this inductor together. So basically now what I'll do, I'll set up a couple of things. Okay, so the first thing that I need, is a signal, and the signal I'm going to set up using this thing here. So okay, so let me set this up here. Okay, so I'm going to use this signal generator in order to give me some sort of signal over here, and so here is the output of this signal generator. So as you can see, I have to connect the input of the signal generator to the inductor, and then the ground goes to the resistor. Okay, so this is my input, goes to the inductor, and the ground goes to the resistor, and this is the resistor end. Okay, so now that's basically done. And now I need to watch the input voltage, meaning I want to watch the input signal that is coming in here, and also the output signal that is going out here. So I connect this to channel 1, and I connect this to channel 2 on my oscilloscope. So this is channel 1 on my oscilloscope. I connect it to input. connect this to input, and this of course goes to ground, and I connect channel 2 to my output, which is this point, and I connect it to ground. This is the exact same circuit that we have basically drawn over here. Okay, so now if you take a look at the oscilloscope here, there is a couple of things to show here. So you see that this is my input, which is basically the input coming in, and this is my channel 2, which is output, this one over here. So my input signal is basically so my input signal is 10 volt, around 10 volts peak to peak. My output signal is about 10 volts peak to peak. Okay, so now you want to actually increase. So you said that over here, what happens is that you have to increase your signal so that the voltage drops, and the voltage drops over here, I think somewhere around 100 kilohertz or something like that. So let's see where it drops. But before I do that, I want to basically make the amplitude of this signal 10 volts peak to peak. So I make this 10 volts peak to peak here. Okay, 10 volts peak to peak, and then so now this is 2 divisions times 5 is equal to 10 volts peak to peak, and the output over here is the exact same thing, 10 volts peak to peak. That means that the filter has not basically the voltage has not dropped yet, right? The voltage is still somewhere over here, it hasn't dropped yet. So I increase the frequency over here. As I increase it, you see that the output is still not dropping. So I go to 10K, for example, and still not dropping. So 100K, still not dropping. 1 megahertz, and now you see that your output is dropping. Okay, and you see that your output is about, so let me make the input 10 volts peak to peak, and 10 volts peak to peak, and my output is actually 1.4 volts, 1.4 vertical division. So 1.4 times 5 is equal to 1.4 times 5 is equal to 7 volts peak to peak. So this is 10 volts peak to peak. This is 7 volts peak to peak. So my input is 10 volts. My output is 7 volts. Now one more thing that you need here is your frequency. Your frequency is if you take a look at your signal here, you can see that your frequency is somewhere about so this is one complete cycle of your signal. So this is 1, 2 point. Let me bring this down so we can actually see something. And this is 1, 2, 2.6. 2.6 horizontal units is one complete cycle. So 2.6 horizontal units times the time base, which is 0.2 microseconds. So that's 2.6 horizontal units times 0.2 microseconds is 5.2 into 10 raised to the power negative 7 seconds. and if you take the reciprocal of that, it's going to be 1.9 megahertz. And as you can see here, my signal generator is set to 1 meg. The multiplier is 1 meg, and then here I'm past 1.8, so the frequency that we calculated is right. So it's 1.923, for example, megahertz or so. So I note down these values. So my the frequency is 1.923 megahertz, 923 megahertz, and the voltage is V of in is 10 volts peak to peak. V of out was what was that? 7 volts around. So 1.4 times 5, 7 volts peak to peak. Okay, and then the only thing that you need here now is the value of your resistor. So I disconnect this circuit from here, from the oscilloscope and everything, and I have to measure my resistor on a multimeter. So if I'm on ohm and ohm, so the value of my resistor here is 990 ohm. 990 ohm. So R is equal to 990 ohm, and that's basically all that we need here. So now we can do the calculation. Okay. So now if you get rid of this thing. Okay, so now I have these values over here. So my frequency, the frequency was 1.923 megahertz, and the input voltage 10 volts peak to peak, output 7 volts peak to peak. And this is important. You want to get your circuit to some area of the frequency, to some value of the frequency where you have a lower output than the input. This is something that you need to do. Otherwise, you will get garbage value out of your calculation, because you would get something. You would actually, this would be some. I mean, if the input voltage, the problem is that if this input voltage is, let's say that your input voltage is equal to your output voltage, then this is going to be equal to 1. So 1 squared is going to be equal to 1 squared is going to be equal to 1. 1 minus 1 is equal to 0. So then your L is supposed to be equal to 0 here. So it doesn't work this way. And the commercial, basically, the commercial, I suppose the commercial inductance meters, they have a microcontroller inside them, and then there is a program, and in the program, basically, it's specified that, for example, if the value is such and such, then use this frequency, and if the value is such and such, use that frequency, and so on and so forth. And there must be a little chip inside there that creates different frequencies. I mean, different signals with different frequencies, and then it must, I mean, the way that it works, it must be like that. Otherwise, when you want to do it manually, you have to basically do everything manually, basically. But it's, I mean, it's not going to take you much time. Once you know what you're doing, then you can simply do it probably in a few minutes probably. Just simply very quickly set up your oscilloscope signal generator and hook up everything, and then do a couple of measurements and then put it in this formula. So then anyway, you have to basically get your basically you have to get your signal to your frequency to such a state where your output voltage is a little bit lower than your input voltage, so that your output is not garbage value. Okay, so then now that we have this thing, we have V of in, we have V of out, we have the frequency, and we have the resistance, so we can calculate the inductance. So now in order to calculate the inductance here, I'll use this calculator, and it's equal to R over 2 pi F. So R is 990 ohm over 2 pi F would be 2 pi times the frequency, excuse me. Okay, so times the frequency, and the frequency was 1.923, for example, megahertz, which is times 10 into times 10 raised to power 6, and then you want to multiply that by the square root of basically V of in, which is 10 volts over 7 volts, and you have to raise that to the second power minus 1, and that is going to give you 8.3 into 10, 8.35, 8.36 into 10 raised to power negative 1, which is weird. That's going to give you, so L is going to be equal to 8.36 into 10 raised to power negative 5. So if you write this as 836, and then basically 1, so 1, 2, 3, 4, and one, two, three, 4, 5. Okay, so now this is in Henry, right? This is now in Henry. So if you want to have that in microhenry, for example, you would simply multiply it by micro into 10 raised to the power negative 6, and that would give you basically 1, 2, 3, 4, 5, 6. So that is 83.6 microhenry, which is okay, which is right, because the inductor that I have over here is 100 microhenry, and this is giving me 83 microhenry. So when you read something off of your oscilloscope, of course on an analog oscilloscope you cannot make very precise or accurate readings, so that would be one problem. And moreover, your signal generator is also important. If the sine waves that it generates, if they're not, most of the time, for example, right now the frequency was about 2 megahertz. Now the signal generator that I have can go maximum all the way up to 2 megahertz. So when I drive it all the way up to 1.92 megahertz, the sine wave, the output gets kind of distorted and deformed. It's not a perfect sine wave anymore. So So that's also one problem. So I mean, all of these come together, and then of course again your readings on the oscilloscope are not perfect either. You want to basically, if you want to do a precise and accurate measurement, you want to do it on a digital oscilloscope, for example. But otherwise, this method is going to give you a good way to measure the inductance of an inductor using a simple oscilloscope and a signal generator. Now there is one more thing. Now here you saw that the value of this the inductance of this inductor was about 100 microhenry. So I needed only about 2 megahertz in order to drive the circuit to the area so that the output voltage could drop, meaning that I had to basically drive the frequency high enough so that the output voltage was, for example, somewhere below the input voltage, so I could basically do the kind of calculation that made sense, right? Now, so the value of this inductor was 100 microhenry. Now if you have, I have taken this inductor over here out of this is an SMD inductor, and the value is 10 microhenry. Okay, so 10 times smaller than, 10 times the value of this inductor is 10 times smaller than the value of inductance of this inductor. So for this kind of inductor with this value 10 times smaller, you need a much higher frequency so that your circuit gets into that area where basically the output voltage is lower than the input voltage. So for example, for this inductor I tested actually, and the frequency that I could use was about 8-9 megahertz or so. Okay, so you need to be, that's also one thing that you need to have. And then of course probably if you want to go all the way to, if you want to basically measure the inductance of inductors all the way up to 1 microhenry or so, or 1 microhenry or 0.1 microhenry, probably 50 megahertz or so would be more than enough as a signal generator, as a signal source. Meaning that the frequency that you would need there for an inductor of, for example, let's say 0.1 microhenry or so, then that would be around, I think 50 megahertz or so would be more than enough for that kind of thing. But so that's basically it. So that's basically how you can measure the inductance of inductors using an oscilloscope and a signal source. I hope that you enjoyed this video, and I'll see you in the next one. Thank you.